Hello, it's Keith here and welcome to lesson 1 of my platform specific tutorials. And what these are going to do is each lesson we're going to take a specific task and we're going to learn how to do that on each of the different hardware platforms we're going to be looking at. And obviously each system will have its own different firmware and hardware requirements, so that task will be different for each machine, but we're going to write common functions that we can call and use in the same way on different systems. And today we're going to be looking at basic text and screen functions. So what we're going to do is we're going to create a clear screen function. We're going to create a locate function which will move the cursor, some print character and print string functions, and we're going to create a function to read a key from the keyboard. And we're going to do that on the Amstrad CPC, which you can see up here in the top left, the ZX Spectrum in the middle here, the Enterprise 64 or 128 top right. Bottom right, we've got the MSX here, and on the bottom left, we've got our most simple system, which is the TI-83 calculator. So we're going to create one common piece of programming code, which I'll show you here. So this is a common piece of code that runs on all the systems, and just by changing these compiler directives here, we can enable one of these to compile to that system. And the way that we achieve this is we have written specific code for those platforms that deals with the intricacies of those systems but works in a common way so that our common code can use it without worrying about which hardware we're compiling for. And that's really the secret of creating a good multi-platform piece of software without too much debugging, is to create modules, kind of like drivers, that will deal with the hardware and then just use those drivers in the code. Now we're going to be doing much more complex code today, so unlike last time, I'm not going to be typing in as we talk through it, because the debugging tools on systems other than the Amstrad CPC aren't as easy to use, so it's probably not realistic, and also we're going to cover a lot of code in a relatively short amount of time. So let's begin. First of all, let's have a look at let's just have a look at what our program's actually doing. So you can see here, first of all, we're clearing the screen, and then we're setting the cursor position, and we're using HL for the cursor position, and H is X and L is Y in this case, and the top cursor corner is 0. So top left is 0 on these machines. Now obviously the screen size of the machine it varies quite differently. Most of them are at least sort of 32 characters wide, but on the TI-83 it's not even that. So we can't really do much about that, but we can at least make sure that the top corner is 0,0. And then what we're doing is we're going to print a string, which is message. And like last time, the print string command is virtually identical to last time, so it's character 255 terminated, so that's our message. So we print that to the screen. We do it 3 times, moving the cursor each time, just to get this kind of this sort of ladder effect here, and that's just to prove that the locate command is working correctly. And then we tell the user to press a key. We use this new line command to move down a line. Then we wait for a character from the user, and we print back the character that the user entered. And then we've got this shutdown and start init command, which are doing some stuff that those systems need to get them ready for a text screen. Now this tutorial is going to be using the firmware to do all of these operations. Generally I don't advise that if you can avoid it, because using the firmware means that you've got more risks involved with regards to what is the firmware doing with your registers. You've got memory limitations, what banks can I page in and out and things. But for this kind of beginner lesson, we want to be able to get things working as fast as possible, so we're relying on the firmware to do most of the work for us. Later on, when we get more advanced, we will be able to create our own sprite font, where we can create our own common font for all of these systems, send graphics to the screen in a common way. We can create our own input routines, and if we want, we can mimic the same names of the functions and the same functionality of the functions. So our sprite-based locate routine works identically to our firmware-based locate routine that we're going to be learning today. So starting simply with the firmware, and then sort of once we're more confident, once we've got more skill and more software, we can break out into a much more advanced routine that uses sprites to do the fonts in the same way. So I don't think it's too much of a problem that we're starting using the firmware today. Let's begin anyway, and let's have a look at the Amstrad CPC version. So I've created a kind of structure for my directories here. So if we have a look, so you'll see you've got these src folders, and these are the source, and these are what we're going to be looking at today. Res stands for resource. There aren't really any of these, but that would be things like sprites and music. Build is temporary files relating to the compilation of the code, and then rel is for release, which is the final disk images, the final tape images for the software itself. Now, the compilation scripts I'm using here, I'm going to try and make available to you. Unfortunately, they're not quite finished yet because it's taking a lot of testing and configuring to get it to all working right on everyone's machines. But I will make this available to you, so please look at my website because I'm hoping it will be on the website within the next week or two. So anyway, so we're going to go into source CPC here, and the one we're going to look at is functions, because this is doing all of our basic firmware functions that we're going to look at today. So here is the start of the file, and you can see with regards to the CLS command, we're actually just using a firmware function call at BC14, and because we're calling this, rather than creating a label and a call command, we're actually just using a symbol here and defining CLS as being memory address BC14 in the firmware, and that will do the job. And print char as well is the same. We're just using this BB5A function call, and wait char as well, we're using BB06. So yeah, we've got three of our tasks done immediately with just 3 lines and no real code at all. They're just definitions. Now locate, the firmware call is slightly different. The top corner is actually 1,1. Now because we want it to be 0,0, we're having to inc H and L before we call the firmware function call. And then we've got this push pop here just to protect the value of HL, so that when we return back to the code, we haven't that required change by the firmware has been hidden from the program itself. And then new line on the Amstrad CPC, as most systems, we use a character 13 and a character 10, which is carriage return and new line. And there we go. And then with print string, this is exactly the same as our previous time that we've looked at this routine in the main beginner lessons. So we just loop through the memory address passed to us in HL. We print each character until we come to a character 255, at which point we return. And that's everything that the Amstrad CPC version requires. Now, part of the reason it's so simple on the Amstrad CPC is because I write all of my code first on the Amstrad CPC, because as I've said before, I find WinApe the easiest assembler, debugger and emulator for a beginner to use with programming. So I try and make it easy on myself. I work on the Amstrad CPC first, and then I branch out onto the other systems where maybe the debuggers aren't quite as powerful, and certainly there isn't a built-in assembler. So let's move on from the Amstrad CPC now. And let's have a look at the enterprise thing as it's next. So here's the enterprise version. Now the enterprise is here. This is a rather obscure 8-bit system from the 80s. It wasn't very successful in the UK, but it probably should have been, because it's quite powerful. So I've been trying to have a look at it, and I'm hoping to include it into these lessons, and I'm hoping to release my game on it one day. So let's have a look at it now. Now, the Enterprise has a fairly advanced operating system built into it, and it works in something called channels, which is where you open a connection to a device such as the keyboard or the screen, and you sort of send data to it or read data from it. Very much like the sort of .NET Stream functionality, but so it's quite different to the Amstrad CPC version. There's a lot more code. And there is a large init routine for getting the screen working, which we're not going to look at today. But anyway, let's make a start on the functions we are going to look at. So the init routine will have loaded up channel 10 as being the screen and channel 11 as being the keyboard. So just bear in mind that you would need to look at that init routine as well if you wanted to see this. And all of the source code will be available on my website. So if you really want to get into the detail of how to get the enterprise screen working, please look at that, or just look at my Hello World example, which uses the same code that I put onto YouTube before. So print char, we protect BC because we need that to stay the same to maintain comparable functionality to the Amstrad version. Now then we load the character that we want to print to the screen into the register B, we load A with the channel number, and then we call OST6, which is sometimes called, you will sometimes see as EXOS in people's examples, and even the debugger actually does that. The reason for that is they've created a macro to rename EXOS to OST6. Now, I don't tend to do that because I want to show the real commands that are running, but that's just something to bear in mind. If you see other people's examples, you might see OST6 called EXOS. So we just call that, and then the byte afterwards is a command number, and so command number 7 says write a byte to channel A, and that's all we do for print char, so that's not too bad. Now, print string is basically the same as before. The only difference is the print char command I've replaced with these commands here, and that's just to do the equivalent of this, but I've embedded it in the print string command so that we don't do more push pops than we need to. So that's just it's just a slight change I've made there. And now next we've got the new line command. Now on the Enterprise, new line is basically the same as the Amstrad CPC. We send character 13 and then character 10. Now just to kind of speed things up a bit, rather than calling the print char command twice, I've actually created a sort of string of the characters here, and I'm using the write block command where we can specify the number of bytes in VC. And this maybe is a little bit faster, maybe it's not, I haven't tested it, but at least it does allow us to show the use of the write block command, which is where you send a number of successive bytes to a channel on the Enterprise. Now, wait char will wait for the user to press a key and then return it in A. On the Enterprise, we've got channel 11 as the keyboard, and command 5 will read a byte from the channel and store the result in B. Now, because our Amstrad CPC version needed the byte returned in A, I have had to copy B to A, and then I'm using this push pop here to just protect the BC register from being affected so that this version matches the Amstrad CPC version. It's quite nice actually. The Enterprise operating system, this EXOS call, doesn't alter any of the registers at all, which makes our life very easy. But unfortunately, because you're having to use A for the channel number and then B for the data, even though it's not altering any of the other registers, it is affecting more registers than the Amstrad CPC version did, which didn't affect any at all. And when we're working with code we're going to use in a common way across multiple platforms, we need to make sure we know which registers are being altered, which are being corrupted, and which are being kept the same, because we need to rely on, we need to know which ones we can rely on not having been changed by the functions we were calling. Okay, so that's our wait char routine. Now our clear screen routine is a little bit obscure. This is again done by sending text characters to the screen, and it's kind of some function characters. So we send the escape and then this control Z character here, which are represented by hex 1B and hex 1A. So just like we did with the new line, we're sending a block of 2 characters to the screen on channel 10, and that will have the effect of clearing the screen. A little bit strange, but it does work just fine. Now here we've got a definition of our write block command here. Probably actually not worth calling that. I could have just put that in there, but I copied this from another example, so it's ended up in there like that. Now our locate command, a little bit more hectic here maybe. In the same way as the clear screen command, we do the locate by sending a string of 4 characters to the screen. So the first one is this escape code, and then actually it's an equals symbol, but it never actually appears as an equal symbol. The screen channel will process it and know that it's a relocation command, so the equals will never appear, and neither will the numbers we send following. So we send escape equals and then Y and then X, and that will move the cursor to the correct location on screen and then show following text in that location. So because we're having to send 4 characters rather than doing 4 print char commands, which would be quite wasteful, we've done this write block of 4 bytes, and then that will do it. But because we've used so many different registers here now, we're actually having to protect quite a lot here. So yes, that's not ideal, but never mind. And also quite strangely, there's some special rules for for the locate command on the Enterprise. So on the Enterprise we add hex 21, and that will make the Enterprise locate command work the same as the Amstrad CPC locate command, which is what we want to do for this sub-function to work with in the same way with our other systems. And here we've actually got all of the rest, which I'm not going to cover today. This is all relating to initializing the Enterprise screen memory. I did cover this a little bit more in my Hello World on the Enterprise example, and we will probably look at it later in more detail, but today I just want to focus on these common commands on all the systems. So that's the Enterprise version, and let's have a look at the MSX version now. So on the MSX you can see we've got print char, which is just a firmware function. It's hex A2, which is in the low memory area. And then we've got wait char, which is at hex 9F. Again, two very simple commands which actually do the exact same thing as on the Amstrad CPC. So we're sort of very quickly there. And clear screen isn't too bad either. The only thing with the clear screen command is it requires the accumulator to be 0. So we've done XOR of the accumulator, which is our quick way of loading the accumulator with 0. Then we jump to C3, which is the CLS command. So that's quite easy. C6 is the locate command, but just like on the other system, we do the top cursor coordinate is 1, 1. So to match our expected functionality of 0, 0, we're inking H and L, and then we're just calling that firmware function, and then we're protecting H and L just to make sure that they return from this locate command in the same state as we sent them. New line on the MSX is a character 13 and a character 10, so we're just using print char to do that. And print string, very simple, just using print char over and over again. That's it. So that's nice and easy. Shutdown is disabling interrupt and halting. That's to stop the system, and that's because on the cartridge-based systems we can't return to basic. So I'll just cover that quickly. So nothing too exciting on the Enterprise. So let's have a look at the TI calculator. Now the TI calculator is our most limited system we're covering. It's fallen asleep, so let's turn it back on. So this is the most limited system, and you can see its screen is actually very small. I'm not sure how many characters that is. It's maybe 20 or 16 or something, but it's a very, very small screen. So obviously we can't make it work exactly the same as the other systems, but we can at least give ourselves a start by making the commands we've defined work in the same way. So on the TI-83 calculator, this RST5 is often referred to as bcall, and this is actually why I don't like using these defined macros, because everywhere I went online I saw the command bcall being used, which is not a Z80 command, and they kept referring to this bcall, and I couldn't find it, and I had to search around for half an hour to find the include file that defined what bcall was. So rather than using macros and include files, I try for these basic tutorials to just actually use the Z80 commands, so that there's no possible confusion when you're looking at this. You know exactly what the Z80 is really doing. If you want to use those kind of macros, I'm not against them, but for these basic tutorials I want to show you the real commands. So RST5 is a big call. It's a far call. What it does is I believe it pages in the ROM of the calculator, and then calls this memory address in that ROM. So it reads the 2 bytes after the RST, uses them as a jump address, switches the ROM back off, and then returns to your program. So these 2 bytes are kind of swallowed in by the RST5, but it's effectively calling this address in firmware. So that address in firmware will clear the TI-83 screen. And then our locate command here, well, the locate command's very different. We don't call anything at all. There are 2 variables in memory at these addresses for the Y and X location of the cursor. We just load them in, and that does it all for us. So I guess next time we do a print command, the TI-83 firmware will look at those addresses and go, well, that's where I was printing to last. So that actually does the job for us. Print char, we've got this this command which does do the job, and we just need to protect all of our registers because the firmware will overwrite them if we don't. So to make sure when we return back to our program we have common functionality with that print char command on all of our systems, we need to protect these registers. Wait char as well, there's a nice firmware function here. Unfortunately though, because of the odd way the TI-83 calculator's keyboard works, pressing number 1 won't necessarily come up with a number 1, and things like the letter A, you actually have to press shift and press it. You would actually have to process the commands more thoroughly. you'd have to read back what the key had been pressed and then translate it based on what numbers, whether you were expecting numbers or letters. So we're kind of doing a very crude job here, but I thought it was enough just to get started. And on a later lesson, I've actually written a joystick input routine which works on the TI-83 calculator and which has a redefine keys function and then emulates a joystick. So if we're looking to do gaming, then we don't need it, but if we were looking to do text input, then you would need to have some handling of that alpha shift key to allow you to get text or numbers depending on what you needed to do. So a new line, we've got a special new line function here. Sending character 1310 does not work. Sending character 13 doesn't work. You have to use this special new line function. So that's a good reason on the TI-83 calculator why we've got a function to do a new line command and not some kind of defined character string that we send to the print string command, because on the TI-83 the print string command cannot do a new line character. And then here we've got our print string command, which just does the exact same as on the other systems, just repeatedly uses the print char command to get the text on the screen. And there we go, that's the TI-83 calculator. Now, considering what a strange system it is compared to our others and what a limited system it is, it's actually quite minimal, the amount of code we've had to do to get it to work. It seems to have a quite powerful firmware, even if it is heavily limited in screen space and RAM. So finally, let's have a look at the ZX Spectrum. So on the Spectrum, we have a firmware call to do our clear screen. It's at 0D6B. The locate command is very much like the enterprise version. We're sending special character codes to the screen, and the first one we have to do is send character code 22, which it's rather strange on the Spectrum. You may have seen a Spectrum keyboard that it has these. I'll just show you. So you'll see on the Spectrum, the keys actually have these sort of commands on them, and each of these commands is actually a character in the character set, which is kind of odd, but that is the way it has been programmed to work. So what we're sending is character 22, which is actually defined as the @ character, if you will. So the screen firmware reads that character and then understands that the next two characters that are sent are actually going to be a screen location, and then moves the text cursor to it. And that's what we're doing here. And then again, we're just protecting all of our registers so that we don't cause any negative effects to the rest of the program when we're compiling for the Spectrum version. Now, new line on the Spectrum is just a character 13. There's no character 10. It doesn't like receiving a character 10. So what we do is we load A with 13 here. And then you'll notice there's no jump to print char or call print char, because print char is actually next. So we're just kind of letting execution flow through into print char, and that saves us a jump command. So that's quite nice. And then print char, we have to open the stream number. We have to open channel 2. On the Spectrum, there's sort of two streams for the screen. There's the top screen, which is the main bulk of the screen, and then there's a one-line bottom screen, which I believe is down to the sort of 48K where memory was limited, and the bottom screen was used for sort of for data entry, and the top screen was used for showing your program that you were working on. So we're selecting the top screen, which is the main one, and then we're sending the character with OST2 here, and that will do the job for us. Very nice. And print string is the same. We're just using that same channel open with by selecting stream 2. We call this function here, which will open the channel, and then we're doing a loop here, and we're just repeatedly running OST2 to send the characters to the channel. And then when we're done, we just restore our registers here and then return back to the program we were running. Now wait char is kind of similar. You'll see here we're protecting our registers as always. We're loading a different stream. Stream 0 is both the bottom screen when you're writing to it or the keyboard when you're reading from it. So we select stream 0 and then we open the channel, and then we just call this read byte command, which will read a single character into A, and then we go back to our program, and that's the Spectrum version done. So there we go. And you can see here that we've got a few different ways of working with things. The Spectrum and the Enterprise have this kind of channel stream kind of concept of opening connections to devices and then sending data to them or reading data from them. Whereas the MSX and the Amstrad, at least don't present that to us from in the firmware sense. We have these very simple firmware functions that do all the work for us. And then the TI-83 calculator is a bit different again. It's basically the same way the firmware does it all for us. There's just a few slight oddities on the TI-83, and I think there is really just down to the fact that it's a very limited system with very little memory. So it just has to sort of make a few changes to the way it works to accommodate that. But they're all very good. Now, what I haven't done is I haven't shown you the program working. So let's just give it a go now. So we're running it from the disk because these scripts create onto the disk and into memory simultaneously. So you can see we've got this ladder of hello worlds. And then if we just press the 8 key, you'll see it says you pressed 8. Okay, so that's the CPC version. Well, let's just have a little play here. Let's recompile the TI-83 version, and just to prove it's actually recompiling, I'm going to change this to Hello World 777. So we'll just compile that. So you can see saved to build program bin. And now if I get up my virtual Z drive here, and then if I run TiGo, just hit enter here. Hello World 777, Hello World 777. So you can see that the recompiling has just worked. And then if I press the 8 key, you can see it doesn't come up as an 8, and that's because it's coming up as a key code. So you'd probably need to create some kind of translation table here. But anyway, I think that was an adequate beginner example of how to read the TI-83. As we're on a roll, let's just do the enterprise version here as well. So if I just rem out this TI-83 and then rem this build enterprise. And we've got two options here to run from a disk image or from file emulation. So we'll run the disk image and hello world. And you press V. So there we go. You see that works as well. And again, the important thing to just understand is all I'm doing here is removing the comment from one of the lines in this list, this ZX Spectrum here, commenting out the others, and that tells these scripts here to load in the correct functions to control that system's firmware. And because those functions work in a common way, all of this code here is absolutely identical, never changes, and that allows us to write one program that works on multiple systems in the same way. And that's going to be essential if you want to develop a game for multiple systems, because it's going to reduce your debugging time and your development time just by miles and miles. So it's definitely the way you want to try and program if you want to program for multiple systems. And I mean, of course, you're going to have your own sort of time constraints and your own goals in programming. But for me, if I can write one program and release it on 5 systems, then that increases the value overall of the development time that I have to invest in that. The result is 5 times if I'd done it for only one system, but the development time is probably only 2 times the actual development time of just working for one system. So in my opinion, for me, it's definitely worth aiming for more systems if you can, if you're interested in it, of course. You know, there's no point if you don't like these other systems, but I think it's good. And the other thing is, if you've written your code in a way that works on 5 systems, you can be pretty confident that your code is designed solidly, that it's bug free, because you're kind of putting it under a stress test where if you've made any mistakes in your code, if your design has any flaws in it, any weaknesses in it, you will find them because you will be unable to get it to work on the more limited systems, or your code that worked fine on the Amstrad, maybe it was corrupting a piece of memory you didn't know about, and that piece of memory may be far more important on the Spectrum. So by developing for these multiple systems, you will really push yourself, and you'll really see if your code was as robust as you thought it was, because you will find out that, well, it doesn't work as you expected. Now, as always, the source code for today's lessons is going to be available on my website, and very soon I plan to make all of the development tools available on my website. I just haven't finished the debugging yet, so please visit my website. There's a new page for these tutorials. They are split off from the main ones. These are called the platform specific series, but the documentation is very much the same as before. So we've got all of the versions of the program here. with details of how they work, just like we've covered today. So please go and take a look at that. Please download the source code. Let me know what you think. I'm planning to do more of these as soon as I can, but they are very time consuming because I'm essentially having to develop and test 5 times for all of these different systems that I'm covering. It won't be possible to cover the TI-83 in all cases because it's such a limited system, but the other systems I am going to cover every time. So when we come to disk loading or sprite showing, you will get an Amstrad CPC routine, a Spectrum routine, an MSX routine and an Enterprise routine that will work in the same way, and that will allow you to target all of these systems very easily. And also, hopefully, I'm hoping that this website will become a good, easy access point for people who are looking to do the basics on these systems. When it came to me looking up the locate command on the ZX Spectrum, I had to spend about half an hour searching Google for it for some reason. I'm sure it's on every website out there, but I just couldn't find it. And I ended up finding my own website before I actually found the answer. So I'm hoping that I can make the platform-specific series answer the beginners' questions on programming these platforms. You know, how do you do this on the Spectrum? How do you do it on the MSX? I'm going to make the answers all there as easily as possible. Please like this video and follow my channel if you want to. Let me know what stuff you want me to cover in the future in the comments. I'll always do my best, but of course it is very time consuming, so I may not be able to. I can't do really crazy complex things, especially if I don't already know the answer, which in a lot of cases that could be the case. So anyway, thanks for listening today. Goodbye.